So the next question we can look at is number 5. The basic idea is that it's a normal form game. Have to figure out what the Nash equilibrium is, if there is any. So the way I usually do this is we're going to look at blue's perspective first, and blue is going to assume or guess that green is going to play Sherlock. So blue is choosing between these payoffs, 12, 11, 10, and 8. Out of that set, 12 is the most attractive. We then move on to assuming that green is going to play Watson, and here blue is choosing between 0, 1, 5, and 6. 6 is the best payoff possible, so in response to Watson, blue would play Wilma. So we've done both sets of strategies for blue. Now we're going to do it for green. So we're going to start off by assuming that green thinks blue's going to play Barney. Here you're choosing between 0 and 6. 6 is better. Then we move down. What's the best response if blue plays Betty? We're looking at 1 versus 5. Out of those two, 5 will dominate. Then we move green down and assume that that blue will play Fred. Here you're looking at 2 versus 3. Across those, 3 is dominant. And last, we're going to assume that blue is going to play Wilma, and best response is going to be comparing 3 and 0. Out of those two, 3 is dominant. So a couple things that come out right away. There's no little combined strategy where both people want to play it, right? None of those boxes contain 2 circles. So there is no pure strategy Nash equilibrium. The other thing we can see is that there's no dominant strategy. There are 2 strictly dominated strategies for blue. They will never play Betty, they will never play Fred, but that doesn't tighten up the game enough to get any different results. So that's it for the first part of the problem. So for part B, we're going to look at 2 different sequential games. The first option is that firm B goes first. I've made firm B green just to make it easy. And to solve a sequential game, we're going to start at the last round and work our way back towards the present. So if blue sees that green has played Sherlock, blue is choosing across 12, 11, 10, or 8. We know that means blue will choose Barney. So this is going to be a little bit of abuse of notation because it's not exactly right to do this, but just to give you the understanding, if green plays Sherlock, they know Betty will not be played, Fred will not be played, and Wilma will not be played. So when they look through, all they have to think is, if I play Sherlock, blue will play Barney. You can think of that entire tree collapsing down to that single node. Now we can walk down to the lower node and assume that green has played Watson. Blue gets to make its choice. It's choosing across 0, 1, 5, or 6. Out of that set, 6 is best. And again, same abuse of notation. We're going to cross out everything that we know blue will not play. And so when green looks down the Watson tree, it has collapsed down to a single possible outcome of Wilma. So green now gets to make its choice. If it plays Sherlock, it knows blue will play Barney, and it will get 0. If blue plays Watson, if green plays Watson, they know blue will play Wilma, and they get 0. So no matter what B does, they will get 0. So if B goes first, payoff equals 0. So that's it for the first part of that one. So the next case that we're asked to consider is, what if green refuses to go first, then blue will go first. So again, we're going to start at the end of the tree and work our way backwards. We're going to start by assuming that blue plays Barney and green has to make its choice. If that happens, green is choosing between 0 and 6. They will choose 6. If blue plays Betty and green sees it, green is choosing between 1 and 5. They will choose 5. If blue chooses Fred, green is looking at 2 or 3. 3 is better. Finally, if blue plays Wilma first, green is choosing between 3 and 0. Between those two, 3 is better. So again, abusive notation, but it's not the worst thing to do in an exam. We know that if blue plays Barney, green will play Watson, so we can get rid of the Sherlock. If blue plays Betty, we know green will play Watson. We can get rid of Sherlock. If blue plays Fred, green will play Watson, get rid of Sherlock. If blue plays Wilma, green will play Sherlock, get rid of Watson. So now when blue is looking through and trying to figure out what its first move should be, if it plays Barney, it knows green will play Watson, and here's the payoff that it's looking at. If blue plays Betty, it knows green will play Watson, here's the payoff it's looking at. If blue plays Fred, it knows that green will play Watson, here's the payoff it's looking at. And if blue plays Wilma, it knows green will play Sherlock, here is the payoff that it's looking at. So now blue's choice is across 0, 1, 5, or 8. Out of those, 8 is the best possible outcome. So if A goes first, we know the play will be Wilma, comma, Sherlock, for a payoff of 8, comma, 3. What you can then do is compare the 3 if A goes first to the 0 if B goes first. So pretty clear 3 is better than 0. So the solution to this is firm B will refuse to go first. Why? If B goes first, payoff for B equals 0. If A goes first, payoff of B will equal 3. So that's pretty much how you get to figure out part B of that problem. So the last part is we're going to go back to our simultaneous move game, and hopefully I haven't destroyed the graph too much. No, it still looks good. So we'll do part C up here as well. Firm green is just terribly confused, and I'm sure you can be sympathetic to that problem because game theory can be awfully confusing. They give up, and they're just going to toss a coin. That's fair. So 50% of the time, they're going to choose Sherlock, and 50% of the time, they're going to choose Watson. So actually what's kind of nice is you don't need to build out an entirely new table. What I'm going to do is figure out the payoff for 1/2, sorry, it's green's move, so we'll keep them green, 1/2 half of Sherlock plus 1/2 of Watson, because they're playing a mixed strategy. So the payoff, if they go half Sherlock, half Watson, for blue, we're running out of colors, is going to be half of 12 plus half of 0. So if blue plays Barney in response to half-half, their expected payoff is going to be 6. And again, that's half of 12 and half of 0. If blue plays Betty, then we're going to move to the next row. The expected payoff is going to be 1/2 of 11 plus 1/2 of 1. So that's also a payoff of 6. If blue plays Fred in response to the half-half strategy, it's going to get an expected value of 1/2 of 10 plus 1/2 of 5. That is 7.5 is their expected payoff for that. And last is if blue plays Wilma in response to half-half green. Sorry, that was in the wrong spot. If blue plays Wilma in response to half-half green, they're going to get half the time they'll get 8, half the time they'll get 6. That's 14 by 2. That is also 7. Well, I guess not also 7. It is 7. Since green has already determined what it wants to do, it's basically punting because the question is too confusing for it. We don't really have to figure out their payoffs because the only person choosing a response strategy is blue, but we might as well do it anyway just for the practice. So if green plays half-half and Barney is played in response, they get 1/2 0, 1/2 6. Their expected payoff is 3. If green plays half-half, blue plays Betty, the expected payoff for green is 1/2 1, 1/2 5. That's 6 by 2 or 3. If green plays half-half, blue responds with Fred. Expected payoff for green will be 1/2 2, 1/2 3. That's 5 by 2 or 2.5. And finally, if green plays half-half, blue plays Wilma, green's expected payoff is 1/2 3, 1/2 0 or 1.5. And again, these payoffs for green, I'm mostly doing just so you can see it solved again. We don't need that to figure out what will happen. Green has chosen the strategy of 1/2 Sherlock, 1/2 Watson. The only person who has to make a strategic decision here is blue. So when blue knows that green's going to play half-half, it's looking across 6, 6, 7.5, or 7. Out of that set, 7.5 is best. So we've got in part C, I'll tuck it right here and hopefully it's not too small. Green plays half-half. And that's, again, horrible notation, but whatever. And the best response function for blue is going to be Fred. All right, and those are both strategies, so that should be blue's strategy equals Fred. And the expected payoff for the two are going to be 7.5 and 2.5 is the expected payoff for the two. So that is your answer over there. So hopefully that works.